Well, I thought I was going to giving a Blackboard talk, but I thought this might be more effective to deliver the idea because there are a lot of figures to draw. So this talk is going to about an observation of some ground state wave function that arises from consideration from a particular quantum error correcting code. But I'm not going to talk about quantum error correction at all. And this exemplifies a state where previous concept of RG and MERA really does not apply. So here is a concrete example that you might want to consider further. So let me just explain what the model is, and later on I will give what the RG calculation was. This is a spin model defined on the three-dimensional lattice. And there I put 2 qubits per each site. The interaction term is crazy. It's product of 8 Pauli matrices, one of sigma x type and the other of sigma z type. And each of the term is product of operators arranged in this form. This model is exactly solvable in the sense that each term commutes with one another because, for instance, if this interaction term were placed at here, then this vertex will meet, but there is no overlap. And if the interaction term is placed along this edge, then there is an anti-commuting pair, but they appear in the even number. That's always the case. It can be meet at a phase, but then you will have, again, even number of anti-commuting pairs. And this model has a property that is shared with many topological order systems in the sense that it has a locally indistinguishable ground state. More precisely, it means that if you have some arbitrary local operator, and if you know that that operator commutes with Hamiltonian so that it acts on the ground space, then it must be a product of terms in the Hamiltonian whose eigenvalues are already known to be +1. So it should act as a just scalar multiplication, which is trivial. And one very peculiar property of this model is that you can separate, well, it's all about the isolating excitations. On the left-hand side,
before I go into this, so there's another local operation we can do. You can imagine you can insert a layer of a product states.
Layer of product state.
Yeah.
Okay.
So you have a 3D cube model. You can imagine you can add just one layer, 2D layer.
Okay.
Now this 2D layer, you just put the product state there.
Okay.
Then there is an issue. Is that kind of local operation, or can you absorb such a layer into this cubic code? So what I try to say is that this seems could be a distinction between this cubic code and the quantum Hall state, for example. The quantum Hall state seems you can insert a line of a product state and somehow scramble things, and the quantum Hall state can absorb this line into it.
Absorbs?
In the sense by doing some local unitary transformation. But I wonder whether if you do this kind of adding some product degree freedom, well, the cubic code will be different. That is somehow cannot absorb it. So basically, my question is following: is that well, the local unitary is the only local operation, or one can generalize that into by adding this product states also is kind of generalized local operation.
Oh, I see. So your question is, in the previous slide, I only consider the local operator to act on the given lattice, whereas if I introduce ancillary degrees of freedom and act on that, what would happen? That's your question.
Yeah, that's right. Yeah, that's basically. Whether this, if you just do local unitary like a quantum circuit things, they are locally indistinguishable. But adding ancillary system may respond differently.
So adding an ancillary system amounts to having a non-unitary operator, but also some arbitrary operator on the system. But this calculation doesn't depend on that.
I see.
So, well, given any linear operator,
Okay.
it doesn't have to be unitary, but you can decompose it in terms of linear linear combination of unitary operators.
Okay.
And for each of them, this holds.
I see. I see. So I think this maybe also have the stability against adding this ancillary
Right.
resistance.
So let me coming back to talk. Let me contrast the phenomenology of this model with the conventional things. And the conventional thing, I chose the conventional 2D toric code. Here you had the similar interaction terms. It's one sigma z type and sigma x type living on a square lattice of 2 dimensions. You have a point-like excitation, and if you apply certain local operation that forms a string, then you can arbitrarily isolate your point-like excitation. However, in the cubic code case, there exists a point-like excitation, and the separation is possible, but the process is different. Process must be taken in this very complicated fashion. You have to do some self-similar operation such that in order to separate these red dots for arbitrary far away.
What's that stuff that's left behind, the blue bits?
Blue bits are the points where operator you have act, and the red dots are the violated terms in your Hamiltonian.
But that's just some unobservable change in the ground state, like the dashed line on the left.
Right. This itself is unobservable. What is observable is the red dots. However, in order to obtain such an isolated configuration of excitation, you have to go through some complicated process.
Can you create a string excitation using kind of like a membrane operator?
Yes, you can, but
Is that a fractal or it's not
No,
fractal?
it
Oh,
does-
I see. String can be created without fractal.
yeah, the
But
string
the
can
point
be
has to be fractal.
right.
I see.
That's right. And because of that reason, as an application to the quantum memory, then it has a pretty long memory time, although it does not diverge with the system size. And you can interpret that as a slow dynamics from the ground state to some thermal state. You need some relaxation time that depends somehow on the system size, although it has a maximum value that is independent of system size. But it's qualitatively different behavior from the previous models.
So compared to 3D toric code, it does the maximum value be e to the beta around the beta square?
Right. Okay. That was a brief overview of the cubic code. And another strange thing, under the periodic boundary conditions, or L by L by L, then the degeneracy is always a power of 2 with some integer exponent. But the exponent as a function of system size is a crazy function. It's not a smooth function at all. And the formula I can give you is this. The exponent k is given by degree of greatest common divisor of these three polynomials.
And the omega is?
Sorry?
What's omega?
Omega is third root of unity over binary field. So it's not an exponential of 2 pi I over 3. It has nothing to do with that. It's just some algebraic number defined over.
And t? What's t's for?
T is just a formal variable just to count the degree. It has no physical meaning. At least you can read off this calculation quite easily, because if the system size is a power of 2, maybe it's a fun calculation. Over binary field, this seemingly false formula is true, because all the intermediate term will have some coefficient that is a multiple of 2, which is 0. So in here, A could be 1 or omega squared. If I raise it to some power of 2, then this whole, but 1 plus 1 is 0. So you have some constant times t to the power 2 to the power t. So every vector will have a t to the L vector. Therefore, the degree of will be that L.
As system size grows, there's a there's an envelope which kind of traces the maximum degeneracy. What is the envelope looks like?
This is 4L.
4L.
Yeah.
So it's algebraic, not exponential.
No. Well, it's the k is algebraic, but the total degeneracy is exponential of that. So
So in terms of a system, linear size system, it has
exponential of diameter.
Of the linear,
Right.
rather than the volume.
Right. So the entropy per volume vanishes.
I see. But what is this form? And could you write down as a linear as a linear exponential? So what is there's some number there. Do you know the more precise asymptotic form?
Oh, well, already for this family of system sizes, you have a exponential. So the degeneracy in the maximum size, it will be 2 to the 4L, roughly.
So 2 to the 4L.
Yeah.
16.
So let's look at the wave function, the original goal of this whole analysis. And we generally look at the entanglement. However, speaking of entanglement is quite ambiguous terminology because we could define an entanglement entropy for arbitrary bipartition, but there are exponentially many such a possible bipartition, and we don't want to work with that huge set of numbers. So we need some more refined or more coarse set of numbers or objects that we can develop our understanding. Right, and I insist that those entanglement of the ground state must be understood in terms of some renormalization growth flow. And just to remind you what the RG is, it's just a process where first you group a set of nearby qubits and then choose a correct representative qubit for each block. And you compute the effective interaction or effective entanglement among those representatives. And so the question of the analysis of RG relies on how would you choose the representative for each block. And for this analysis, I demand the representative to be unitarily related to the corresponding block. So I'm allowing myself to apply arbitrary unitary to that particular block, and I will pick out one particular. So just to repeat, local entanglement, I don't want to focus on that, which amounts to say that I can apply arbitrary local unitary transformation. So this defines equivalence relation among states that you want to understand. If they are related by local unitary, then we demand that, we assert that they are equal. And in order to choose a right representative, the guiding principle is that we want to disentangle as much as possible. So if you apply some unitary and discover that for your choice of unitary transformation, among 4, say 2 qubits are disentangled from the at rest, then I can safely throw this away because these definite qubits will be anyway, does not affect the long-range entanglement pattern. To it is not guaranteed that you will be able to pick just single representative. You might have to pick 1, 2 or more qubits to represent entanglement with other blocks properly. And then after choosing the right representative, I will rescale the system to recover the length scale. So let's do it for the familiar state, the toric code. If I work in the sigma, if I work in the basis where sigma x is in the diagonal, then the ground state consists of loops. And the way to understand that is if we start with some product state and then applying one particular blockhead term, that will introduce some loop in the ground state. And since my Hamiltonian demands that ground state to be plus one eigenvalue of this operator for all of them, I should superpose them all to have the plus one eigenvalue. So my ground state will be the soup of such loops. The loop, as long as it's closed loop, there's no length scale other than the short distance cutoff given by the lattice constant. So if I find some unitary such that I make the loop into a point, then I can forget about that point. So indeed, if you can do this calculation precisely and discover that 2D toric code is actually invariant after discarding such a disentangled qubits. And the same is true for Letterman model and the quantum double model. So all known examples of topological order systems in 2 dimensions are entanglement, renormalization, fixed points. And this gives rise to the so-called MERA description, where you start with a single qubit, and then you apply certain products of local unitary transformation. In the quantum information language, it's just a quantum circuit of bounded range. And then you expand your lattice. And then you insert some ancillary qubits into the lattice, and you apply another layer of quantum circuit to the new system, and you expand the lattice, and you keep doing it. And in the end of this process, you will get your desired state. I read the description of MERA in a reverse order. Usually, you will learn the MERA starting from the actual state and apply unitary and throw something away. But I can equally understand it in the reverse order. Now, let's get back to the original problem of cubic code state. And just as the toric code state was a soup of loops, the ground state of cubic code is also a soup of something. However, I cannot give any geometrical interpretation for that object. It consists of some sphere-like thing, but it has some crazy fractal-like thing. I don't know how to name it. I just call it something. So here's the result. The result is very simple to state. I found a quantum circuit of constant depth, although depth is quite large. It's 32. You have 32 layers of controlled knots. And discover that after the application of this becomes a tensor product of two states, one of which is exactly the same as before, defined on the coarse lattice with the lattice constant 2a, if the a was the lattice constant of the original lattice. And something else that is not equal to the original. But this one can be, it turns out to be a ground state of another Hamiltonian. And the Hamiltonian, before describing that, I can do the same analysis for this extra piece that is newly discovered. Then I find another quantum circuit of depth about 100 that disentangles this new ground state into two copies of itself. Remarkably, the two copies are the same as before. except for the length scale. And the new state, the promised new state, is a ground state of this Hamiltonian. The Hamiltonian lives on the cubic lattice with the 4 qubits per site. And the interaction terms are, there are 4 types, 2 with sigma x, product of sigma x, and 2 with product of sigma z. Again, they are all commuting, exactly solvable, and the ground state is precisely this. And the phenomenology at the very crude level is identical to the original cubic code. It has very funny degeneracy formula. It has point-like excitations, although isolating them would require very complicated operation. And it has degenerate ground states on which there is no local observable. This bifurcating renormalization group flow directly leads you to the tensor network description, which is called branching MERA, where normally you would have this branch. Now you have multiple branches at every level. Well, the construction of understanding the branching MERA is the same as before. You start with some qubits, but not now single qubits, but several of them. You apply some quantum circuit on each copy independently, and you expand the lattice, and you merge them. You apply another layer of a quantum circuit, and you expand the lattice, and you keep doing it. And in the limit of this process, you will get the desired state.
So actually, you never get rid of the original copy. It's always what we do with this original model.
Original model, well, yes, original model will be in one branch, and all the other will be the new thing.
You mean original cubic code can be represented by MERA with only one branch?
No, original cubic code state lives on the very bottom.
Yeah.
But if you apply the disentanglement transformation, then you have to describe it as a tensor product of 2.
Okay.
One of which is the same as before, but the other is not.
I see. So on the top level, can you say which one is the original one? Maybe the other few is the new one? Do you have that picture?
Well, the ground space is isomorphic to the tensor product of the whole thing because I only apply unitary. However, the description of each branch, the original one is contained in the single thing, and all the rest is the newly discovered, the new model with the more complicated interactions. You might wonder about the entanglement entropy about this branching MERA. So let me derive the entanglement upper bound of the entanglement entropy by understanding the MERA first. Well, you started with a single qubit, and you have applied a quantum circuit that is of constant depth. That will increase your entanglement entropy for a given block along the boundary. So you will add at most this much. Later, you are expanding the lattice, so your effective linear dimension of your region has increased. So if you apply another layer of quantum circuit, then the additional contribution will be of this form, where the linear size is doubled, again, along the boundary. And you keep doing it. So in the end, you will reach a region whose linear system size is power of 2, where the exponent is the number of layers you have applied the quantum circuit, and the original length scale that you started with. So, well, entanglement entropy for a box is upper bounded by contributions from all of those. It's just a simple sum. And it turns out that this formula. So if capital D is 1, which means we are working on a line, then this sum is logarithmic. Well, this factor is just constant, and you have logarithmic many terms. However, if you go to higher dimensions, where D is greater than 1, then exponential factor easily this is a geometric sum, so it's bounded by area law. And the same thing, well, I'm sorry. So what if you had a multiple branch? Then you will have this contribution for each branch. So you just multiply the number of branch at that level, and you just sum them over. So in the cubic code case, where the branching occurs, the number of branches is 2 to the t, where t is the level of your RG. And the dimension is 3. So if you plug in here, then the number of branches is not too fast to kill your area law. So although you have branching, since the number of branches is sufficiently small, you're okay. You're still in the area law regime. Surprisingly, if the dimension is 2, then you are not allowed to have more than one branch at each level, as long as your state obeys the area law. So the branching, the gap, and all these things becomes consistent when you go to 3 or higher dimensions. So how did I calculate those? Like a depth 100 quantum circuit. How did I obtain them? It will be brief. However, well, I can deliver the main idea. So the Hamiltonian is frustration-free, and the ground state is defined by this stabilizing equation, where S is any of those terms in the Hamiltonian. So if I apply certain unitary operator on the ground state, then I can find analogous stabilizer operator, obviously, by this trivial equation, by conjugation. And if I found that this conjugated operator turns out to be a Pauli operator acting on a single qubit, then because of this frustration-free condition, I can immediately tell that that particular qubit must be disentangled from the rest. Otherwise, I would break the frustration-free condition. So I will try to find some unitary such that my stabilizer will be mapped to a single qubit operator. And there's another fact that is special to this Hamiltonian, that it is the sole information that we have to care about lying in the information about the position of sigma x and sigma z operator. And since the Hamiltonian is translation invariant, I don't have to address a whole lattice. I can just focus on the local terms. Well, another brief detour towards our explanation method, that if you have a bunch of ones that is related by translation by 1 unit, say in this case to the left, 1, 1, 1 is translated to the left, how would I describe this matrix? All I have to carry is the arrangement of ones here. So I introduce an auxiliary, perhaps meaningless, or physically x represents translation to the left. But anyway, I write down some power of x whenever there is 1. And the position of that 1 is encoded in the exponent. And I place a placeholder, which happens to be a plus sign, and I write down the matrix in this form. Well, because I started with the translation invariant matrix, the resulting polynomial, the next one is obtained by multiplying x to the previous one, because that will raise your exponent by 1. So all I have to remember is this one for that translation invariant matrix. The same thing can be applied for lattice Hamiltonians by this correspondence. Previously, we had one direction of translation, say to the left, but in the lattice, we will have multiple directions, to the x, to the y. and to the z in the 3 dimensions. So I associate a coordinate with the monomial whose exponents are encoding the given coordinates. So suppose I am required to describe this Pauli operator. Sigma x acting on this point, and sigma z acting on that point, and sigma y at that point. Then I can just write down a polynomial whose upper row describes the sigma x part. So sigma x part appears at 0, 1, 0, which is encoded here. X to the 0, y to the 1, z to the 0. And sigma y up to phase vector is a sigma x times sigma z. So I can interpret it as having a sigma x component at this point. And this point is, according to this description, is just z. And plus is just a placeholder, well, implicitly meaning that they are multiplied. And for the sigma z part, I have nothing at this point, but have something and that. So again, sigma y is decomposed into sigma x and sigma z. So I have to write down this, representing this point. And this coordinate is translated to this monomial. And I again placed a plus placeholder. So let's do this exercise for the toric code model. I have to define my unit cell because square lattice with the qubits on edge is equivalent to having a pure conventional square lattice with 2 qubits per side, where the unit cell is associated like this. Then I have a 4 by 2 matrix where each row describes the labeling inside the unit cell and whether it is X or Z type. So going around the one particular operator, I write down accordingly monomials and place the plus sign as a placeholder. And since there is no sigma z part, I just write down 0. And likewise for sigma z operator. So this matrix captures all the information from your Hamiltonian. Cubic code, we could have this representation, or we could have this diagram to remember the positions of sigma x or z, or equivalently, we could just write down a polynomial. They are all equivalent notations. Here, bar means that all monomials have opposite, the minus exponent. So you see, a sigma x operator, it has a almost inverse parity, spatial inversion. So that's why the bar appears. So now I have a very compact description of my Hamiltonian, so I can do calculation on top of it. And you can work out that any CLIFFORD operation, meaning that a unitary that maps a Pauli operator to another Pauli operator, can be written as a row operation on that matrix. So you just apply some row operation on this matrix to find the equivalent representation in the Hamiltonian language. And another interesting operation that you should do is that you should take a coarse translation group. Originally, we had one unit of the translation was encoded in this monomial. However, because I'm going to do the RG where the length scale is double, I had to reinterpret my translation group to be a smaller one. And according to that, here's a prescription. Given any polynomial in an entry, you just replace x with this matrix and y with this diagonal one, and z with that. This corresponds to the taking enlarging your unit cell that combines one at the origin and one at the X position. Well, this is just technical detail. You don't have to worry too much about it.
Does this correspond to a sequence of CNOTs?
Not yet. Well, so sequence of CNOTs corresponds to some row operation, but
This is just adding figures.
right. But in this description, you can only have a sequence of CNOTs that whose periodicity is equal to your original lattice periodicity. But we don't want that because we are going to apply unitary on the super block, which breaks your original translation structure by a little.
Then this replacing F with this expansion, this is not the cross-graining, it's the opposite of a cross-graining transformation.
This is cross-graining.
It is.
It is. So,
Oh, I see. You're going to put together both sides. So,
right. Right. Well, if you had to say, if you had an Eisen model, just bear in mind that in pure Eisen model, then here my translation is, this Hamiltonian is translation invariant by translating one unit of lattice spacing. However, I could take a unit cell to be a 2 qubits. But in that case, I would have to write down the two kinds of interaction terms. This is one interaction term that acts on inside my unit cell. Well, the circle 1 and circle 2 means the one particular qubit inside your unit cell. And there should be another term. That couples the nearby cells. So you really need to increase your description of matrix. Once you realize that, then the calculation should be done on your computer because I'm going to dealing with a pretty large matrix. It's almost like a 64 by 32. So I wrote a mathematical script where my Hamiltonian is encoded in the matrix, and all my product of CNOTs is written as a script. And later on, after a lot of CNOTs, you discover that the original model and something else. Input, taking the new model as an input, I again do some CNOT and some basis change. And I finally discover that there are exactly two copies of the original model. And this is the way I could do the calculation of that 100 quantum circuit. Otherwise, I wouldn't be able to. Okay, so I have briefly reviewed some properties of the qubit code, and by representing them into a compact form, I was able to calculate some unitary transformation such that your ground state becomes a tensor product of the two, one in which is similar to the original, and the other is not. And for the other one, there's another quantum circuit that disentangles into two copies of itself. And this directly leads you to so-called branching MERA description for your ground state. So my interpretation of this phenomena is as follows. This is not a very strong statement, but the bifurcation is because qubits in the block that you have grouped are so entangled with the outside so that you cannot choose a single representative from that block in order to represent properly your entanglement structure. And interestingly, that happens at all scales. It doesn't converge to our conventional picture. And this suggests that the notion of RG fixed point, at least in the scheme of entanglement RG, is quite a subtle matter. Thanks for attention.
Thank you.
Is there a way
Questions?
to modify this network so that it goes so away from this fixed point? Like, is there a way to modify the model to represent something like you reduce the scale in RG?
Oh, so your question is, can I modify the model slightly so that this happens again?
So that something happened in the network, like they cut out.
Oh, that part I really don't know. But that's a pretty important question because this only addresses a single, say, fixed point, and it doesn't address how it will behave in nearby Hamiltonians. Right, that's a very important question. But unfortunately, I don't have an answer.
Frank?
Can you understand the Grotze degeneracy from this RG?
Yes. Well, you need an extra ingredient. I mean, each point here must be degenerate too. But if that is given, if we know that these points are degenerate, then I tensor them. So the degeneracy should multiply. And as you go down the level, you have to multiply all together.
Okay, and that gives you exactly the situation of 2 to the
Yes.
L.
Yes.
And 2 to the L plus 1, you have like a unique
To the-
for
Right.
what happens there.
Yeah, that part is tricky because if your system size is not a power of 2, then how would you group them into 2? It's not a bipartite lattice. So this requires you to consider only the system sizes that is power of 2.
Another question there.
What would happen if you take not just a three-dimensional, but a stack of two-dimensional layers?
Well, in that case, you exactly observe this red circle phenomena. I mean, if you start with the two-dimensional fixed point wave functions and you just stack them, then obviously, if your blocking includes at least 2 copies of it, then you should have some branching. So branching itself doesn't tell you much. However, in this blue diagram, this function and that function are different. That wouldn't happen in the stack set.
Yeah. If you compute the topology in time entropy, and I imagine it's no longer constant. Like the
Yes.
extract, or maybe there is some kind of linear term. Basically, again, what try to say, if you try to view this as stacking, the topological entropy should have some dependence on the size, the shape of the boundary. But whether this cubic code would have some similar behavior.
Well, there is a very crude, not an argument, a crude calculation along that. You can think of a topological entanglement entropy with respect to the partition of solid torus. But the contribution, I mean, the subleading term next to the surface, the boundary term, depends on the orientation of that solid torus. So,
This model.
yes. So in that sense, it's pretty similar to the stack of toric codes. However, the direction of stacking doesn't really match with the lattice directions.
But can you identify a direction for stacking? I mean, there's a certain orientation where you can see the topological entropy scale in linear direction with that particular direction.
I think that is possible.
Oh, there is such a particular direction.
I think so.
Oh, I see. That's kind of commensurate with lattice or some kind of intercommensurate direction.
Well, I didn't put it forward too much because the notion of entanglement entropy in higher dimensions is not really well defined. So,
Okay.
There are no further questions. Thank you again.